Good afternoon, and welcome to Cambridge. I won't give you my life story, which I seem to remember last year I spent half of my allocated time doing. Being a Cambridge graduate, it always is sort of fun to come back here, actually, although it certainly is a much busier place somehow, it seems to me, than it was in my day. You know, this talk, actually, I have to say, is sort of a little bit of a revamp of a little sort of concept project that started off some months ago, really in connection with the IMS, you know, the International Micro Symposium, which is in Phoenix. I've sort of been a bit of a regular traveller to Phoenix over some years through doing quite a bit of work with Freescale, their power, obviously power amplifiers, LDMOS, fab, and so on, and modelling group there. Someone had it. This actually started off as an internal thing, where they wanted to sort of set up a kind of they wanted a sort of a fight between proponents of sort of XParameters and behavioral modeling. You know, this is the big new thing, controversial thing, like most new things are, and you know, the sort of traditional, you know, the old school, you know, with the whole thing, new stuff's a load of rubbish. So they invited me to do the old school sort of side of things, and they invited one of my Cardiff colleagues, Paul Tasker, to sort of promote the new stuff. And I was saying, look, hang on a minute, you know, we do have to sort of live together at Cardiff, you know, and it was sort of, you know, we sort of, you know, do have offices not actually on the same corridor. I think my office is above Paul's office, actually. So I can sort of, you know, make a hole in the floor and drop boiling oil down. We don't really want to do that because, in fact, Paul and I have been drinking beer together for the best part of 20 years. We are very good friends. But we do have a somewhat different view, it has to be said. But I didn't really want to set this whole thing up as a sort of a big fight. And that's the reason that I came up with this title. I'm just simply saying, look, I'm not going to promote this as necessarily being on one side of this argument or the other. But it is, however, what I think. So that's how we go. There certainly are two factions, for any of you who are involved in sort of nonlinear design aspects of things. I realise probably a lot of system designers here where maybe this isn't quite so much of a big issue, but certainly for designing power amplifiers, for example, and a number of other things that involve the use of nonlinear effects in devices. I just started teaching a master's course at Cardiff this last week, where I make quite a big sort of issue about the fact, you know, nonlinearity is not necessarily a bad thing. You know, there's a whole range of devices, applications where we actually make use of nonlinear effects. But of course, they can also be a nuisance where we have sort of spectral distortion and so on. Something which, incidentally, undergraduates find incredibly boring. I don't know what it is. You know, they're quite interested in sort of Class A amplifiers, Class B amplifiers, and you can just about get them slightly interested in power amplifiers. You start talking about, you know, Volterra series and power series and intermods and expanding cos cubed omega t and all this sort of, they're very difficult to keep them interested. They really just don't seem to get it at all. It's quite interesting, really. There are these factions. We are being somewhat bombarded, mainly I think through commercial pressure to sort of take behavioral models seriously, and not many of us are. But anyway, so there I stake my flag a little bit. In terms of sort of designing, there are, as I say, the physical faction and the behavioral faction. I, frankly, have used both, so I'm sitting on the fence already. Physical models go way back to what was originally called the Cripps method, which I think is a term which is still kicked around today. And is still used. I have a copy of the paper I presented my first visit to MTT Symposium, as it was in those days, in 1983, my first trip to the US, where I got offered a job. That was the reason I went, actually. Anyway, the point being, behavioral modeling, in my book, has been around a long time as well, just as long, as what I keep trying to tell my colleagues who want to think this is something very new. The idea of designing tricky things like amplifiers, finding what's the, you know, how do we design an amplifier, the best efficiency, best power. You know, you just basically do some measurements, you know, forget about theory, it's too difficult, it's too complicated, it's lots of maths, you know, just measure it. That has been in fact, when I first started designing power amplifiers, when I got my job at Watkins Johnson in the early 1980s, I emigrated over to California. that was the way power amplifiers were designed. They were designed, you just basically got some tuners and you did some sort of, you found out what the impedances were and you went ahead and you designed things. And, you know, contrary to what I have to say, I do criticize, argue with my colleagues. In the case of Paul, in a very friendly way, usually down at the local brew pub in Cardiff. Yeah, I was saying, look, Paul, you know, I mean, we did actually succeed. You know, all this stuff about, oh, you know, first pass design success. I said, we did used to get that. Not every time, but this idea that, you know, we designed things that always didn't work and required, you know, sort of hours of tuning and all the rest of it, it's not really true. Some things required a few hours of tuning, but then they were ready for production. Once you'd modified the circuit a little bit, that you didn't have to do that every time. You know, you could make a mask, you could modify the mask with all these bits of metal you'd added and subtracted. I mean, it was only a matter of a few hours of work. It wasn't something that had to be done in production. So anyway, as I say, possibly a necessary evil. I'm not sorry to call it that. I mean, we are all, I'm an academic now, you know, it would be nice if we understood the theory that we didn't need to use such sort of, you know, pragmatic methods for designing. It would be nice if we didn't have to do that, but the fact is it's paid a lot of bills. And I'll say a little bit more about tuning, because that's certainly something, another rather controversial issue. I have myself done a great deal of tuning in my life, and still at it, much to the amazement of my young PhD students. My skill under a microscope. It actually seems to have improved, because I think, you know, 20 years ago when I was in the peak of my tuning career, I'd sort of usually drunk about 2.5 bottles of Californian wine the night before. I've managed to get that down to the 1.5 these days. So, yeah, so once again, physical and behavioral. I don't know how to spell that. I think what I'm doing here is, again, I'm sort of, this is sort of the way they spell it in Iceland, I think. I mean, it's halfway between the American spelling and the English spelling. I'm not sure how to spell that. But anyway, is that correct? Oh, yeah, okay, fine. So to summarize, what do I mean by the physical design approach? It's sort of physics-based, essentially, device models, the sort of thing that you can pick up, you know, an icon if you've gone through the process of loading the manufacturer's model, which can sometimes be a little torturous. I'm looking at Malcolm on the front row here. But you can, you know, basically these things are physical-based. You know, you might possibly have a functional description of the IV characteristics, but you know, you're going back to the IV characteristics in order to make a microwave model, and you know that's what most of them do. You sort of add all the various parasitics, you know, the CGS, the CDS, and you may even add in, say, for example, the voltage dependency of some of the capacitors, and that's what we mean by a physics-based model. I have always said and have sort of promoted for decades that you should always work at the device plane if you're doing this kind of design, and is particularly useful in broadband designs. When I first started designing PAs as such at Watkins Johnson in the early 1980s, they were in the ECM business, so these were broadband designs. They were octave band, even double octave band designs, and it is better there to work at the device plane. All of the device parasitics, even the output capacitance, but certainly the bond wires and so on, you treat those as a necessary first element in your matching network. So, you know, you actually effectively almost make the parasitics to be part of your external circuit. It's just that you're not allowed to tune them. You're allowed to make them bigger, but you're not allowed to make them smaller. So you can tune them in that sense. So behavioral model, load-pull-based design has been around a very long time, and here we do tend to work at the package plane. You know, we're taking an entirely pragmatic view of the whole problem. We've got a device in a package, so we just simply say, okay, what impedances does this device want to see at this particular reference point? And as I say, proven success record to this day, still a very widely used, and of course, various companies make some increasingly nicer, better equipment, computer-driven tuners, active load pull systems, and so on, where you can get a good database for your design. So the sort of the red herring on this slide, which I have made red, I didn't actually do that the last time I did it. So that's getting a little provocative, you know, to do that. What's happening is that the sort of the academics, it would seem, have sort of rather taken this concept and tried to sort of, in a sense, go full circle. They're actually sort of saying, well, in actual fact, you know, physics models, you know, are okay, but we hear they don't really sort of work all that well, and you don't ever get first pass design success. And so what we're trying to do here is to persuade you that if we make enough measurements, we end up with something that is basically can replace your device model. So in other words, you make sort of millions and millions of measurements. You can sort of almost set up some kind of a lookup table almost, which does sit reasonably well with the harmonic balance approach, algorithm, whatever you want to call it, to nonlinear analysis. And there is that possibility that you can make enough measurements that you can maybe extrapolate between them and that you can pretty much cover your entire design space. I mean, a very perfectly reasonable goal, I would say. I really don't have a problem with that concept. My problem is that I don't think they're there yet, and unfortunately commercial pressures to get funding both in academia and in industry, people just tend to exaggerate a little bit, perhaps that they're further ahead than they really are. Anyway, okay, so not wishing to bang on about it, work at the device plane, we've already covered that. Fairly simple model really. We tend to assume transistors are voltage controlled current source. It's kind of current sink really, but not worry too much about that. We compute the output voltage using Ohm's law and then start messing around with harmonics and stuff. That's essentially, roughly speaking, the physical approach. As I said, I promised I'd just show you this. This is actually the paper to be, this is from the digest for the IMS, not call that in those, MTT Symposium we called it, in 1983. This was actually in Los Angeles, much smaller event in those days. That's me, Watkins Johnson Company, Hillview Avenue, Palo Alto, California, my golly. And so just a little bit, I'm not going to sort of say bang on about this too much, but I always thought it is quite amusing just to read the first paragraph. The use of load pull contours in the design of solid state power amplifiers is now well established. This is 1983, by the way. The information contained in a load pull plot is of particular importance for broader band designs where exact synthesis of the optimum output load at all frequencies is not possible, and a compromise. Unfortunately, the generation of a set of load pull contours is a laborious procedure if performed manually using mechanical tuners. As a result, several workers have built computer-controlled systems which undoubtedly speed up the measurement procedure, but involve a large capital expenditure in dedicated equipment and setup time which cannot always be justified. So you see, we were sort of at this whole business of doing load pull, and I indeed at Watkins Johnson I was not able to afford such a system. So I sort of had to come up with something else, and this was really where the Cripps method was sort of born really, and I don't want to necessarily describe it in great detail. Everybody knows that if you get to the device plane, a load line resistance, I think we all know that's low frequency electronics. Extending that to allow for the fact that you might actually miss the resistive target, particularly at higher frequencies and when you're working over a broader bandwidth, trying to sort of basically figure out these load pull contours, which were notably never circles. You see, you actually do the measurements, or maybe your device manufacturer who can afford the equipment presents you with his load pull contour. It's never a circle, it's always a kind of a sort of a bit of an ellipse looking thing. So using rather simple reasoning concerning the voltage and the current swing with resistive and reactive loads, it turns out you can construct these load pull contours, which of course are not circles. They're actually two intersecting circles, the area between two intersecting circles. So yes, that was, I suppose, one of these, once I remember quite well sort of thinking about this thing. I'd only been there, I was a new kid on the block, I'd only been there 3 or 4 weeks. I do remember one evening I was actually sitting in someone's hot tub. We were in California, so you had to sort of sample the Californian lifestyle. So I was sitting there in a hot tub and I was actually thinking about this. I'm thinking, well, yeah, resistance is easy. How do you do reactance, and you sort of gradually sort of think about this. So yes, and of course the point about it is that I then ran into what I would call almost a lifelong problem requiring designers to work at the device plane. I mean, it really is quite important to work at the device plane, because if you work at the device plane here, it's frequency independent. Wherever you are, you can actually sort of sweep your frequency and see whether, and adjust your circuit elements or synthesize your circuit so that it stays inside one of these contours. Whereas if you work at the package plane, these things then move in a manner that is frequency dependent. I hope that's reasonably obvious, but I'm just showing a very simple example here. You start putting in actual physical values, of course, you're introducing frequency dependency so that the load pull contour actually sort of now moves with frequency. So my view is it's better to work at plane A where it's fixed and you just simply regard these elements as part of your external matching network. It's much better to do that than it is to try working at plane B, particularly if you're dealing with a broader bandwidth broader frequency range. Just by way, this is a very old example just to show how much difference it can make. This is a sort of a medium power transistor. You work out the load resistance. That's just simply the voltage. 28 volts, you figure 3 volts just for the turn on of the transistor. So you say, okay, in the ideal situation, we got 25 volt swing, and you know, it's a 1 amp divide, 1 amp amplitude swing. So we end up with the resistor of 12.5 ohms, right? That's fine, but that's at this plane here. If you now take account of the shunt capacitance, which in those days was much higher capacitance on an LDMOS device, the capacitance per watt has gone sort of down enormously since this slide was created. But you see what a big difference it makes. I mean, sure enough, if you measure at the package plane, it's more like 1 ohm. This is a little bit getting a little bit academic, but I suppose I threw this slide in because there's a good friend of mine actually who is sort of seems to be appearing at various microwave conferences promoting the idea that RF microwave designers don't understand anything about synthesis. You know, we all ought to go back to school and start learning about synthesis. And it's like, well, hang on a minute, sorry. But we do. In fact, certainly if you're designing sort of octave band, in order to actually come up with the circuit as I'm showing here, whereby the device plane you actually sort of keep this frequency sort of inside this 1 dB contour. The Americans always like this. They call it it's a football. Of course, the Americans look at that and say it's a football. I suppose we could call it a rugby ball. I think rugby ball's a bit more rounded at the edges, isn't it? Anyway, just a little bit of academic point is that the synthesis. This is a Chebyshev. You just design a Chebyshev network, and you can perform this Norton impedance transformation. Possibly these days, this is not so well known. Particularly this Norton's theorem, you know, designing your filter and then showing that although the filter works between 50 ohms, source and load, the fact that you can play around some games, just simply transform these inductors, and all of a sudden, the whole thing works with a 50 ohms down to 7 ohms, which is a very large transformation ratio, and that works over a whole octave band. I do sometimes, maybe this is not taught so much these days, and perhaps it is worth a little highlighting. What is interesting that the Chebyshev design sort of puts the locus into a circle because it's, you know, it's a passive thing. It turns out that if you actually replace the circle with the load pull contour itself, you can actually stretch it. You actually go a bit outside the normal Chebyshev prototype response, and it gives you a significant improvement if you do that. So you can actually end up with you know, a significantly higher transformation. So that's, if you're working at octave band, this is the sort of exercise you have to go through. Much more recently, I perhaps have to just be a little bit wary of the time here, don't I? In fact, yes, I better move on a bit here. I think I'm a bit fast, but anyway. Just now, I'm going to just skip sort of really the next few slides. I'm going to just give you a bit of an overview of some much more recent work that we've been doing at Cardiff under the heading of device plane waveform engineering. We call it waveform engineering. There's quite a lot of things you can do once you start looking at waveforms at the device plane. This is the continuous mode argument, which is really all about dismissing the concept that if you're designing a highly efficient amplifier, you need to short circuit the harmonics. This is very much the classical view of PA design. If you mess around a little bit with some trigonometry, again, Paul Tasker and I in particular, who were mainly involved in deriving some of this stuff, we astonish our students at how we can do trig identities without having to look it up in the back of our maths textbook. You know, we actually had to remember this stuff when we were students. This particular equation here is interesting in the sense it's the product of two factors that do not cross zero. It's sort of almost a little bit analogous to filter synthesis here. What we're actually doing here is we're saying, well, how do we create a family of voltage waveforms that are useful for power amplifier design? That useful feature being that they stop at zero. We call it zero grazing waveforms. And you know, this parameter beta, for example, is entirely mathematical, but when you sort of put it into a context of an RF amplifier, you can actually find that you can design PAs, class A, B, class B PAs, that have the same efficiency but do not have shorted harmonics. We've published quite a lot on that. We call this the class J design space And we even sort of talk about this continuum here as being the class BJ, we call it. There was much debate as to whether we haven't got time for all these little sort of anecdotes, have I, Rose? It's unfortunate. We had a great debate whether we called it JB or BJ. The reason we didn't call it JB was because that's the initials of one of our colleagues who didn't think was really worthy of being remembered in this manner. However, particularly in America, BJ also has some connotations. However, we decided to stay with BJ, actually. And it's sort of really what it's all about is the fact that you can make networks that more or less track the class BJ impedance space and therefore get more efficiency over broader bandwidths. This is an extension of the work which is where we're talking about sort of placing the second harmonic. The thing about class BJ is that design space is that you do still require a reactive component at the second harmonic. So we sort of say, well, if we design a typical circuit, we quite often find the second harmonic is in this area somewhere here, for example. And really all that just simply does is make the mathematics a bit heavier. And what we can end up doing is with these, what we call these clipping contours, we can say, well, if we know where the fundamental is, that's what really defines the power. And you recognize the good old sort of, in fact, I call them sweet potatoes, actually, these, rather than footballs. But anyway, depending on where you are inside the sweet potato, you can draw these things. So, for example, if you're actually at the optimum, it turns out that what this green area represents is you'd better have your second harmonic impedance somewhere in the green region. If you stray over this contour here, you're in trouble. Your waveform will start clipping. So ironically, what it actually means is you're better off if you sort of, especially if you've got a broadband design, you're better off if you actually sort of back off a little bit from the fundamental load line resistor value. Then that gives you a much greater, this green sort of, this sea of green comes, you know, flooding into the Smith chart. And all of a sudden, it sort of hardly matters where your second harmonic is. Well, it's not quite, but that's the idea of it. So you can have all sorts of fun generating all these various green shapes on the Smith chart. And we are actually really still in the process of getting more recognition of that particular. That was reported incidentally in the transactions. Behavioral approach, basically, I think we've said all we need to say on that. Obviously, there are various kinds of tuners. I haven't got time to go into that. There are factions that believe tuners should be passive devices. There you run into problems dealing with modulated waveforms. Then there's the active system, which is much faster. You don't have to sort of move these lumps of metal around, and that is much faster. And they are certainly getting a lot faster. The next paper, I think the next paper is going to be describing a very fast system, and one that I have used. Just want to be absolutely clear about this. I'm not against designing using Loadpull. I've done a great deal of it myself. What I'm sort of not happy about is the fact that we are yet ready to take enough measurements that we can actually jettison our sort of physical models. I don't think that we're really there yet. So I've got to move on a little bit here, sort of talking about sort of various issues with Loadpull measurements. So I'm not really going to perhaps have time to cover that. There is this debate between the merits of active and passive Loadpull systems. They all do have their various pluses and minuses. So let me just get on to what is I suppose, my controversial slide, right? Behavioral models, let's sort of, the main way of getting people to understand what you're talking about is XParameters. You know, we're talking here about the much promoted concept of XParameters. There's been a vast investment, basically, we're talking about this at lunchtime, a vast investment by a leading measurement company. And there has been a slow take-up by the design community. I think that one of the mistakes that the promoters of it have done is to make comparison with the evolution of the S-parameter design method in the 1960s. I do not really, frankly, see that that is a fair comparison. The S-parameter is a much more intuitive approach to microwave design. You're dealing with forward and reflected waves, and I think that that is intuitive. Forward and reflected harmonic waves, sorry, you know, that is not terribly intuitive. I will admit that probably, and I think that in general, power and efficiency, if we are sort of fixed on those two very important properties of a device, probably can be predicted. If you've done enough measurements under enough conditions of output match and input match and bias and so on, if you've done enough of those measurements and you have a way in which you can sort of home in to some point that you've measured that's pretty close to the point that you actually have in your actual circuit that you end up with, I think that there is a reasonable chance that you will get a better prediction than you would using physical models. But unfortunately, as a designer, and I always try to tell my colleagues this, it's not all about power and efficiency. There's a lot of other things that you have to be concerned about, particularly in a multi-stage amplifier, is stability, major problem is stability. Gain, they don't even really seem to be all that concerned about gain, which you certainly are when you're designing a circuit. And I think that in general, this whole thing is a bit of a sad story, I think. There really are factions between the modeling and the circuit design cultures. It is unfortunate that there has not been more cooperation, because, as I say, don't get me wrong, some of these test systems, these pieces of kit that you can buy, are magnificent. I mean, I'll have one. They are wonderful pieces of equipment with which I think, as a designer, I can do a great deal that will greatly help me get better designs and better results. But unfortunately, the modeling community have sort of overstepped the mark. They're telling me how to do my job, and they're telling me that what I do is wrong. And it's like, look, sorry guys, sorry, that is a step too far. But let's work together, This is design flow. Well, I think I've already perhaps said most of you probably can figure this more or less out. I do still start off very much in the Cripps mode approach. I find my device, I figure out what its current and voltage swing is going to be. That's my starting point. Maybe I do a bit of circuit synthesis to actually synthesize the necessary resistance over the required bandwidth. There's this additional business about absorbing the parasitic. You've got to sort of somehow absorb the output capacitance into your matching network. And then we start simulating using the compact model, the physical model, and a simulator. And we start playing around with it a little bit. We do some tuning. If Malcolm can tell me how I can get my tuning button on the screen a little bit more easily. But a very minor complaint. But that's when you start running into other things, such as gain, stability, and linearity, and so on. Tuning, I just wanted to finish up. I have nearly finished. I realise I'm just sort of... Is that 5 minutes, yeah. I just wanted to sort of give you my little pitch about tuning. I, some years back, was working at Filtronic, now not really anymore, and we were from Filtronics, when they were in the base station PA business. And we were making power amplifiers. These were maybe sort of, 50 watt, that's to say 50 watt mean. That's to say probably, several hundred watts peak PA. So it's sort of like, here's the PA. And of course, the thing that works into is a filter. Now, of course, in the case of Filtronic, they make the filter as well. That was actually their main business, was to make the filter. And I was rather interested. It's sort of like, we're always told in the PA, the PA has to be like I'm showing you here. It's a sort of closed box, hermetically sealed. And it's the RF input, RF output, and the DC, and that's it. That's your PA. It has to meet all specs. Obviously you've got to meet power. There's going to be efficiency, and all of these very, very severe spectral distortion. ACP, all that kind of stuff. And it's got to do that in a closed box. So it's sort of like, that's actually, fairly difficult to do. And however, the filter people there sort of say, oh, wow, yeah, we got some really tough specs to meet. We've got to meet, this sort of in-band, in-band attenuation, and we've got to have the cutoff, and we've got to have, out transmit band rejection, have all of this stuff. So that's the reason we need to have all these tuning screws. And I don't know whether any of you ever went to the Filtronic production area. It was an old spinning shed up in Shipley. Interesting place. I mean, you had these people who were literally, I think, sort of more or less, minimum wage. I don't know how much they paid them, but, not qualified people in any way who were basically tuning up these filters. There must have been sort of, I don't know, 20 or 30 of these people. Each had their own VNA, sitting there, and they were sort of tuning these things up, with all these different screws. And I was sort of saying, well, first of all, it was very interesting, actually, some of the stories about how they acquired the necessary skills. They all had these, there were all this folklore about, they used to make certain patterns with the screw heads, which was completely bogus because, the threads were not aligned to the... They made their own screws, actually, in point of fact. I mean, the screws themselves were quite interesting. They actually had a couple of patents on the way they actually made the screws so that they could... There was always this problem with lockdown. I don't know if you've ever actually done anything with screw-tuned microwave devices. It's always probably going to get this sort of thing, sort of tunes up, but then you want to somehow lock it down and it goes off tuning again. They had some rather interesting techniques in that area. But I just couldn't help feeling, I was sort of saying, look, why can't I tune my amplifier? It's like, I mean, here's two components that actually work together in the transmit, box. This one tuning obviously allowed, this one tuning absolutely not allowed, and I never really quite understood it. It's to do with the way we design it, really. I think that the way we do our matching networks, so our microstrip transmission lines and all this stuff, really doesn't lend itself all that well to tuning. I think the other aspect maybe is hermeticity, perhaps, if you've got sort of, transistors are rather sensitive devices, although in all honesty, these were packaged transistors in here. I don't think the enclosure was in fact hermetic. I don't think so. So I'm not sure that that would necessarily be. So I always thought, one of these days, how many days I have left, I'm not sure. I'm going to sort of see whether I can actually figure out a way of designing RFPAs that actually have got external tuning screws so that you can actually sort of absolutely optimize the performance, because there are variations. You put these things into production and yes, the performance does vary. One of the interesting aspects of that variation, incidentally, not giving away any internal secrets, is this whole business about predistortion. I don't know whether Chris agrees with me on this or not, but he's done a lot more of this more recently than I have. But certainly, this was relatively early days of digital predistortion. There was always this puzzle that some amplifiers seemed to predistort straight off, no problem, bang, very good. And yet here's this other one that's made exactly the same way and even seemed to have very similar measured RF characteristics, and yet it would not predistort, for love nor money. And so, there were variations. Just a quick snapshot, which is not entirely, completely relevant to what I'm talking about, but I just thought I'd show you. It's quite a nice picture. One of the things that actually my complete dedication to device plane measurements is such that I initiated a program at Cardiff, which was actually sponsored by one of the large telecom companies actually in the UK, to actually measure the device plane, directly measuring the device plane voltages. And of course, the whole point about this work is, as you can see here, this is a very large transistor. This is a big transistor. This is sort of like 3 large LDMOS chips. I think this whole amplifier, there are 2 of them. It's a Doherty PA actually. When there are 2 of them both firing away full blow, this in fact is about a 400 watt amplifier. So figure this is a 200 watt transistor. And the interest basically was, do we actually see the same voltage all the way across? With this probe here, the whole point about this project was to develop this probe with which we get about 50 micron resolution in terms of actually spatial. As we move along, we can distinguish one voltage from another, say 50 microns away. So we can move along the actual drain of the device here and actually. So this was quite an interesting PhD project. One of my students, one of my more photogenic PhD students, perhaps dare I say, she made it to the front page of the engineering prospectus for Cardiff University, so that's not too bad. She took this photograph, and I was amazed. I said, "How on earth did you take that photograph?" Because it's quite high magnification. And the depth of field there is quite remarkable. She said, "Oh, I used my phone." So I thought, youth of today. Youth of today, my gosh. The interesting thing is that what we're looking at this voltage, some of you will recognize here, we are certainly seeing some modicum of Doherty PA behavior, but it's quite variable across the chip. Not only are the voltages themselves varying very substantially, but the degree to which the peaking amplifier is making this portion flat also varies as well. So we're still very, very much hooked on to device plane measurements. And this is just a little joke slide. I was talking about, people often say I don't say very much about inverted modes. Class F itself, the idea that you have an open circuit has always bothered me. I just thought I'd throw this one in actually, mainly as I thought it was quite an amusing slide. You remember the Hitchhiker's Guide to the Universe, the restaurant at the end of the universe. I always think, you're okay down here. This is relevant, I think, to simulations. This whole business about first pass design success and things that XParameters are definitely not going to do any better job than, in fact, possibly a worse job than we're doing at the moment. The danger is that microwave circuits, whether it's intentional or not, can swing you into this, what I call this very hazardous journey. The right-hand side of the Smith chart is a very, very hazardous place when you're dealing with something that is basically a current source. You can get enormous, strange, weird, big sort of voltage peaks at sort of several times the harmonics that you think are important. The whole academic community seems to have, it almost seems to be axiomatic that only first, second, and third harmonics matter. And certainly in my experience, I think some of the discrepancies, some of the kind of real kind of weird effect, like why is this thing not working? Why do we see this funny dip in our power right in the middle of the band? Why do we see that? In fact, if you sort of basically, that's one of the motivations for doing this work. Because if you actually look at the voltage waveform now, you suddenly see this sort of 5th or 7th or 9th harmonic suddenly appears out of nowhere because there is a component of current at the higher harmonics, and circuits do make this. You can inadvertently find yourself, at this strange part of the universe where the tiniest little bit of current generates an enormous amount of voltage. So conclusions, PA design on output load pool has been paid a lot of bills. CAD nonlinear simulation tools coupled with physically based models have developed and improved slowly, but certainly are now mainstream. This whole behavioral modeling is new. I think it may have a role to play, as I say, but I think it is at the moment quite unproven. And as the next speaker well knows, I am still now in public challenging my own colleagues to actually say, look, let's try it. Here's my transistors. These are the transistors I'm currently using in a circuit design project. Okay, fine. I take all of what you say about XParameters and first pass, fine. Take my transistors. You can have as many as you want, as long as there's not too many. Do it, right? Extract your XParameter, whatever it is, model. Come back, give it to me, I'll simulate my circuit. If it actually gives me a better simulation that's closer to what I measure, I'll be happy to come along to all of these events and tell everybody how wonderful it all is. So far, I've been relaying that challenge, I think, now for 5 years. I did it in public as is it Moro? Sorry, I can't remember your name. No, he will vouch to the fact we had a sort of bit of a stand-up sort of kind of fracas about this, that, they're going to do it, they're going to do it, they're going to do it, yeah, they're going to do it. Well, they still haven't done it. Okay, I'll just give you a quick update on that. Right, okay.
Wow.
Well, yeah, that was a month ago.
I think if we're not careful, we'll be talking till a coffee break time and Miss Liam's talk out altogether. So just 2 questions, please. Yeah.
The very last example you mentioned, I've done it and it didn't work.
Oh, really? Well, so okay. Yeah. I retain an open mind. But
well, I took a device from a PA.
Yes.
And I developed an XParameter model for the device. And I inserted that model into the PA design. Yeah. And I was expecting to see the same results. It didn't work. Yeah. Because an XParameter model is based on a large signal excitation, and then the harmonics are basically perturbed to derive all the XParameters, but that doesn't really work. No. Because this is a large signal phenomenon.
Yes, I know, but I always annoy me because I know a million times I've said it. Measurement-based models are fairly good at predicting the measurements on which they're based.
Yes.
But unfortunately, if you move away, you're in trouble. Yeah. Sorry, I realise we're short of time.
Yeah, one more. Anyone else? Yep.
You talked about continuous modes of operation,
yes.
which assume the device does not clip, the current wave does not clip.
Yes.
Do you think there is a continuous mode which can be exploited once you start to saturate your current and your harmonic design space changes?
Yeah, that is a different problem. I mean, I think that the whole point about staying clear of the clipping region is really based on the fact that we're mainly applications are requiring very high linearity. I tend to think once you start saturating the device, although there may be some applications where that's okay, the power goes down. That's the other thing. Once you start clipping the current, down goes the power, and people don't like that. They like as the Americans would say, they like the bang for the buck. I mean, you're paying money for a big transistor, so if you're going to start driving it, you see the power drops very quickly once you start going to saturation. But yes, the continuous modes do not address that condition. Yeah.
So I was wondering whether the standard efficiency theoretical, let's say 78.5% for class B, they refer for a near region of 0.
Yes.
Right?
Yes.
So if you want to achieve these sort of efficiencies, you're inevitably gonna start possibly clipping your current. Is that correct? I
think that is quite true, and I think it's not widely recognised. Yes. I tend to think if you're going to not clip, you're probably looking at 10% lower efficiency. And if you're sitting there, as you do, you sit there and use your load pull system and you're seeing 75%, you're almost certainly 2 or 3 dBs into compression, which is a problem. You know, I mean, you know, I think again, I know the DSP people would agree with me. Certainly, my experience is, you know, once you get beyond about 1 dB compression, it's very, very difficult to sort of get that back, you know, simply by messing around with the input signal. But there are obviously applications where you can explore. In fact, we are looking at that at the moment, as a matter of fact, for a pulse radar application. But that's absolutely a good point.